So we are going to talk about eigenvalues and eigenvectors. Yes, at the end of the hour you can just put it here. So we said a topic that comes up in a long list of applications in mathematics and engineering has the following look to it, that you have some matrix and you multiply that matrix with some vectors. After you multiply, you get some other vector so y is some output vector. In many cases you want to study the relationship between the input and the output. The special case that happens is where the output vector is just an elongated or the shrunk version of the input vector. So a special case output y is in same direction I'm putting it in some quote because there's some fine print associated with this. We'll talk about that later. Is in the same direction as input vector x. That is, perhaps there is some vector that when you multiply it with your matrix, all that happens is that your input vector doubles or triples or something like that. Here's an example there. So this output vector, if the input was like this, the output is in the same direction as the input. Perhaps twice as big, perhaps 3 times as big, perhaps half as big. So here are possibilities. So it could have been that you multiplied it with x and it became half as large, or you multiplied with the x and became 3 times as large. What we are looking for is a possibility of such an occurrence, and in case it happens, we say something special has happened. That special situation, we are going to label it by this terminology that we say the vector x, the input vector x that plays this role is going to be called the special input vector, and that's called the eigenvector. Eigenvector if you find such a vector, we are going to call it eigenvector, and we said eigen simply means special. And then something else happens. That special vector gets to be stretched or shrunk by a certain factor. That number that shows up in any of these cases is going to be called eigenvalue. So these type of numbers are going to be referred to as eigenvalue. Generic name for them, we don't know what they are going to be until we find them. Generic name for it was going to be lambda. So lambda indicates one such number. So an eigenvalue problem looks like this. Given matrix x, given a matrix A, find x and lambda such that if I take my matrix, multiply with that vector, what happens is that vector comes out just that it has been multiplied by that number lambda. Now we have to exclude a trivial case. if your vector was just 0 vectors here, this would be true regardless of what you put for lambda. If you start with 0 here, a times 0 is 0, and any lambda times 0 is going to be also 0. So to rule out that so-called trivial situation, we put that restriction. Find an x, but don't give me a cheap answer. Truly find it such that it plays inside of this game. Okay, so this is going to be the stuff from which the material in chapter 5 is made. It's going to have some reliance on the topic of determinants that we have studied in 5.1, and all the stuff that we have seen with respect to Gaussian elimination techniques and such, they are also going to come in, and quite a bit of theory also at the very end is going to show itself. So let's go ahead and pick up some examples. Here some simple examples. What do we mean by this situation here? Let's take a matrix A, minus 1, 2, 0, 3, and the vector x is so in this case somebody has already done the hard work and is asking you to check that the given vector x is an eigenvector. Well, let's just go see what is special about this. Let's go ahead and see what is special. So I go ahead and try to find out what's the product of these two. So minus 1, 2, 0, 3. I take that multiplied with 1, 2. What am I going to get? So minus plus 4. So what's the total? I get 3. And 0, 3 times 1, 2. What is the total? 6. Now, is there anything special relationship between these two? This is 3 times that thing. Okay, so this becomes 3 times 1, 2. As opposed to what? As opposed to if I had taken minus 1, 2, 0, 3 and multiplied it with, say, 1, 5. Let me just pull a vector out of the hat. Just multiply, see what happens. Well, let's see what happens. I have minus 1 and 9, 10 makes 9, and this is 15. Is this vector in the same direction as that vector? No. If it wanted to be, if you want to triple this, you should have tripled that one too. 1, 5 and 9, 15 are not on the same line. So if you just pull a vector out of your hat and multiply with your matrix, well, you get another vector. There wasn't anything special about what you started with. There isn't anything special about what you are going to get. It happens in very few circumstances where you multiply and you stay put where you were. Now, once you have one of these special cases, I claim that you can make a whole variety of this. If 1, 2 plays in this game, what other vector could you easily come up with which definitely, without trying, would have the same property? If I go ahead, for example, multiply this thing by, if I triple this, or if I double this, if I double my input, what's going to happen to my output? If all of these numbers are double during multiplication, all of your entries are doubled, and instead of 3, 6, what are you going to get? So just go ahead and try it. Minus 2 and an 8, you get what? 6. 3 times 4 is 12. So you change the input, output changed, but how about the relationship between these two? is saying the output is still triple the input. That is simply property of linearity of this game that we are playing. If you double your input here, this one also doubles. That doesn't have anything to do with playing with eigenvectors. Like here, if I had exactly same matrix, but instead of 1, 5, I go take 2, 10. That is, I double the input here. What do you think I'm going to get? Let's try it out. Minus 2 plus 20, what's that? I get 18. And 3 times 10, I get 30. So you double this, that one gets doubled. That is just simply property of matrix multiplication, because it is linear. However you multiply this thing, the output is going to multiply by the same number. So that property still extends to this, whatever you want to call an eigenvector. As soon as you find an eigenvector, any multiple of that plays the same role. So if I ask you find all the eigenvectors, if you tell me, oh, here I found one, here's I found another one, well, I say, well, you're cheating. This is not really something new. This was already there. You cannot sell that one to me as something new. So when we are talking about these vector x, as soon as you found one vector, any multiple of that vector is going to be also an eigenvector, and it's going to satisfy the same property. So let's write that on the side here. Any multiple of eigenvector x will satisfy same equation. What do we mean by that? I mean that if you take this x and double it, well, this is going to double as well. If you had taken that x and tripled it, and this one will also triple. Those are all going to be eigenvectors. Essentially, when you are finding an eigenvector, you are finding an entire line. You are finding really a line. That's an extension of x. That when you multiply your matrix with that line, you stay inside of that line. Question?
Right there,
Mm-hmm.
where it says 6, 12 equals 3, what is that?
Oh, 2. Sorry, I forgot that to read. This is. Thank you for correction. This is 3 times what we started with. My mistake, I just wrote that one. So the output vector is triple the input vector, just the same way that this output vector was triple the input vector. And we said if you just pull a random vector, that kind of a property is not available. How about what we just said? This vector 1, 2, what does that mean? Vector 1, 2 means you have gone 1 to the right and 2 up. So that is your vector 1, 2. What does vector 2 mean? Vector 2, 4 means, well, you have gone 2 to the right and 4 up. So once this green thing is a vector, essentially every is an eigenvector. Every vector that sits on that line is going to have the same property. So eigenvector is not really a vector, rather it's a, sorry. Sorry for that. So we are really finding an extension or an entire line that has that property. When you multiply this matrix with this yellow line, you stay on that yellow line. It doesn't move somewhere else. Okay, in this simple example, somebody had already found this, and we just checked that what he had fits the description. Majority of the questions is the other way around. That is, go ahead and really find these things. So let's see how does that work. How to find Well, the first thing that you actually get to find is the eigenvalues and then eigenvectors. This one turns out to be a bit easier. That one, this is going to be like the problems you had in 5.1 where you find an X where a matrix became singular. This one is going to require to go back to all that Gaussian elimination and finding roots of certain equations. So let's go back to the same problem and try to play it again. Suppose I'm given the same matrix, -1, 2, 0, 3. I'm trying to find some vector x. Now we are pretending we don't know what the answer is going to be, so it's going to be we don't know, like x1, x2. What we want is that when I take a multiplied by x, I end up with some multiple of that x. That, let me just remind you what these things are supposed to turn out to be. That is, this is like an example of, this is an example of this vector and the fact that it tripled. So our aim is to justify where does that 3 come from. And after we have found that one, so that is going to play the role of the eigenvalue for us. That's the first step. We are going to catch that. Once we have that, then we go ahead and say, well, how can you get that eigenvector? That's the eigenvector we are trying to find here. Okay. The way we proceed, so okay, let's write this thing out. So I say -1, 2, 0, 3 times something I don't know. For now, I'm going to call it vector x1, x2. And outside is supposed to come some other number, a third number, still I don't know, times the same input vector. So we want to find everything that is not a number here. Our procedure is going to first figure out lambda and then something intelligent to say about x1 and x2. I open this thing up. So -1x -1 times x1 plus 2 x2. That's the first line. First line of the right hand side is lambda x1. 0x1 plus 3x2, and the right hand side is lambda x2. Now this is somewhat special in the sense that our matrix kind of extra friendly with the zeros here and such. You're going to see later on how that makes life easier, but for now let me pretend as if it's just some other number. What we do next stage is that we bring everybody to the left hand side, and notice that this x1 is also here, so let me put them next to each other. -1 x1 minus lambda x1 plus 2x2 is equal to 0. Here we didn't have any x1s, and then I had 3x2, and then I have lambda x2 also. Now we are going to go ahead and clean this up a little bit more to make it look like any of those matrix equations we used to solve at the beginning of a semester. For a while, kind of treat lambda as if some familiar number that you can deal with. So that implies that we are going to go ahead and put this thing by collecting the terms a little bit and cleaning it up. So I go ahead and say I can write this as minus, I'm going to factor x1. Tell me what's left inside the parentheses. The other guy doesn't have anything to factor. This thing, I keep writing it so that we get used to proper format. This one, same story as here. I go ahead and collect. So what do I have inside? Now before we go any further, let's just pause here and see. We could have saved a lot of time by bypassing all of these things and go straight from here to here. Tell me what's a quick procedure to, or if you wish, I go ahead and write this thing in the matrix format of it. Matrix format, this entry is -1 minus lambda, that entry is 2, this entry is 0, this entry is 3 minus lambda, times x1, x2. What is the right hand side? Right hand side is just 0. How could you go straight from here to here and bypass all this redundant work?
A times the lambda identity.
Very good, very good. This lambda, you can think about it lambda times identity, or if you see, it's just multiplying from with whatever elements you had here, and it just goes ahead and interacts with exactly that element on the left hand side. So this lambda only gets subtracted from diagonal entries. Why? Because here is multiplying x1, x1 goes with x1. Next, it multiplies x2, x2 goes with x2. If I had x3, lambda x3 will go on the left hand side and just combine with x3, and the other terms don't show up. So here is a shortcut, which is subtract. Shortcut to do what? Shortcut for bringing the stuff on the right to the left. You can simply do subtract lambda from what elements? These are called what? From diagonal elements only. Everybody follow that? So from here, if I want to clean it up, if I want to bring it to the left hand side, lambda just gets subtracted from the diagonal entries, because it's just multiplying those x's. When they go to the left, they only interact with the diagonal entries. Okay, now in section 5.1 we practice this problem. If your concern is to find some x's that makes this 0, there's always a cheap shot answer, which is what? Just pick 0. If you put 0 here, of course you get 0. You don't need to take this course to do that. The question is, what's the question? The question is there a non-trivial answer? Find x other than 0, meaning at least one of the elements got to be non-zero. We emphasize that this is called a non-trivial answer. Very good. We want a non-trivial answer. To get a non-trivial answer, if there is a non-trivial answer, it means the columns of this matrix are linearly dependent. And we said in the section 5.1, without going into the proof of it, that the signature, so we want to find lambda such that this matrix is singular. Really, what the way we come across to that conclusion is that if this times non-zero vector is 0, it means a linear combination of its column is 0. A linear combination of columns of a matrix being 0, of a square matrix being 0, means its determinant is 0. If its determinant is 0, we had another name for it. We call that type of a matrix a singular matrix. So to cut it short, say find lambda such that this matrix is singular. A shortcut to figuring out that the matrix is singular, or a signature of such matrices, is what? So its determinant must be 0. If you want the matrix to be singular, if you want the column to be linearly dependent, force its determinant to be 0. Well, we practiced this last lecture. How do you find the determinant of this? So let's go ahead, find the determinant. What is the determinant of this matrix? In this case, it's kind of easy. We had, what did you do for 2 by 2? Yeah. For 2 by 2 matrices, let me remind you, if you have A, B, C, D, what's the determinant of that? AD minus BC. So here is A, here is D. Don't forget, these are one single component. This is the entire A. This is the entire D. These are the other two guys. Okay, so I multiply the other way and I get a little bit of a relief here because that guy is 0. If it is upper triangular, our determinant becomes very easy. What is going to be left out of here is -1 minus lambda times 3 minus lambda. I stay a little bit smart and don't multiply it out because what? Because I want the determinant to be 0. So since it is already factored, why go mess it up? It's already factored. So I already get my answers. What kind of magical lambdas will do the job for me? Lambda has to be either 3 or -1. Is that right? The solution of this minus. Who is this lambda equal to 3? That is what you saw here. That lambda equal to 3 that showed its head. We were trying to justify where did that 3 come from. So that 3 came from solving some equation. In this case, a quadratic equation. Because this is 2 by 2, it leads to a quadratic equation. If it was 3 by 3, I'll end up with a cubic equation, and so on. Remember, when you solve these type of equation, depending on what degree you got that many roots. So if it's a quadratic equation, you got 2 roots. If it's a cubic equation, you got 3 roots. So in general, a 2 by 2 matrix has 2 eigenvalues. A 3 by 3 matrix has 3 eigenvalues. Various kind of complications could come up, but aside from those complications, the number of special values or eigenvalues you are going to find is exactly the same as the size of the matrix you are dealing with. Now it could happen that these numbers coincide. It could happen that the numbers become complex numbers or unfriendly numbers, stuff like that. But aside from those problematic situations, this is the case to expect. Now we are supposed to go further and find the eigenvectors as well. Who was eigenvector? These would have been the eigenvectors. This is the eigenvector. Let me pause on that and postpone that to the next time. And today I'll just go ahead and do one more example of finding eigenvalues so that we have this one covered. Let's do an example where this is going to be a little bit lengthy. Let's see if we can squeeze it here. So matrix A is 5 minus 7, 7, 4 minus 3, 4, 4 minus 1, 2. So find eigenvalues. And we are postponing the eigenvectors to next time. What was our shortcut? What do? We want determinant of A lambda. When we say A minus lambda, this really means A minus lambda is a shorthand for A minus lambda times I. Who is I? Is identity matrix. So identity matrix, who is identity matrix? Just 1, 1, 1. So who is lambda times such a thing? lambda times this, it just lambdas on the diagonal, and everything else is still 0. So who is a minus lambda or a minus lambda I? Both notations are correct. It means take that and subtract that from it, which we said verbally, subtracting lambdas from the diagonal. So 5 minus lambda, let me open it up. This is minus 7, 7, 4, minus 3, minus lambda, 4, 4, minus 1, 2, minus lambda. So I subtracted this from that. Now hard life starts. You have to get the determinant of this thing, and well, what do we do? Let's copy it through so that my copy here is going to be first so I am going to go multiply these, multiply these, multiply those, and then come back up, go the other way. So multiply, let me not cover it so that, and then these, and then these, and the other one. So what we have is 5 minus lambda, minus 3 minus lambda, 2 minus lambda, this is for this, then plus minus 7, 4 times 4, this one is 7, is that 7? 7 times 4 times minus 1, so I went this direction. Now I'm going back up. This is going to be minus 7 times minus 3 minus lambda times 4, that is this one, then minus 5 minus lambda, 4 minus 1, going this way, and finally minus 7, 4, 2 minus lambda. Now, in the interest of brevity, because we are running out of time, well, this has to be calculated, and has to be calculated carefully. These problems are typically cooked up so that final equation that you get is at least slightly friendly. If you make any mistake in any of these places, things do get to be nasty, and just about everything is going to be lost. So let me just bypass that stage and ask you to simplify, and then you get some equation like this. We are going to encounter 3 by 3, occasionally 4 by 4 matrices, and yes.
Because you do a minus lambda, you should be at a different sign in the book, which is lambda minus a. It's just the sign.
Let me do a correction. So here, since I'm doing a minus lambda as opposed to lambda minus, this is gonna, good point. So I'm gonna get minus lambda cubed plus 4 lambda squared plus 7 lambda minus 10 equal to 0. Thank you. My mistake. This was off by minus sign, but it does not influence what we are going to do next. Next, we need a little bit of practice with stuff from college algebra. How do you solve cubic equations or higher powered equations? If the problem wants to be nasty, there is really no easy way to handle these kind of equations. So you have to look for kind of easier answers, manageable ones. And one of the tools that you learn in college algebra is the so-called rational root theorem. That if you have a polynomial and you have cleaned it up and you want to guess, perhaps it has an easy root, the easy roots are, possible easy roots are the ones where numerator of that rational root is a factor of this constant and the denominator of it is a factor of this one. But luckily, this one is always 1, so I don't need to worry about it. That means the only numbers that are possible easy roots of this equation are factors of this. Well, what are the factors of number 10? 5 and 2. Well, we have to be a little bit more careful than that. What else could be? It's a little bit, even though we're getting some shortcuts, we still have work to do, which is 1 and 10. What else? Unfortunately, there's a long road ahead. It's like any of these numbers could possibly be a root, and also possible that none of them is a root. Okay, so you have to check to see if any of them is a root. Luckily, the problem is designed so that you are not going to be off track or spending too much time. What's the very first number you try and happens to be the root? 1. You can tell that 1 is a root if the sum of all the coefficients is 0. Minus 1, plus 4, plus 7, minus 10 is 0. That means if I had replaced lambda by 1, I'll get, okay, I got 1 root. If I am really lucky, perhaps one of these guys is still a root. Maybe it is, maybe it isn't. We got lucky once. It wasn't necessary for any of them to be a root, but typically it is. Question is, once you got a root, excellent. What we do is do a long division or a short division, dual division. Sorry, we're running over. So you have to take minus lambda cubed plus 4 lambda squared plus 7 lambda minus 10. If you're saying lambda equal to 1 is a root, it means one of the factors is what?
Lambda minus 1.
Excellent. Lambda minus 1 has to be one of the factors. And the question is, well, what is the other factor? And your long division is going to tell you what this factor is. Once you found that factor, you set it equal to 0, and that is going to tell you 2 more roots. Okay, let me postpone this thing for you guys to do by Friday. We pick up this and continue it from there. Okay. Now make sure you return your test before you leave.